you all had a good weekend. Let's go ahead and start first with a word of prayer if we could. Could I have a volunteer to offer that for us? Please.
Our dear Heavenly Father, we're so grateful for this morning and this new week that we have to start fresh for school, and please us that we will be able to have a clear mind, that we will take in the information that we need, and please us that we will be able to concentrate and trust the teacher, and please us that we will continue to work hard in school and do the best that we can. And we see these things in the name of Jesus Christ. Amen.
Thank you. Okay. So, all right, your first assignment, as you all know, is due tonight. Again, that's by midnight tonight, and then turn it in electronically through Learning Suite. Okay? You don't have to turn in the autograder or your output from it or anything else like that. That's just a little prototype. Remember I mentioned it's a proto-grader, as I kind of call it. The intent of that autograder is not to fully run every test case. The TAs, again, will be using grading scripts, but we want to make sure ahead of time that that they can run the grading scripts on your code, and that you're not penalized if for some reason the output is coming out in the wrong format or something. So that's why we give you this little sort of stub of an autograder with a few test cases in it, but again, you need to be testing your own code. Now for this one, the functions are all so simple that it's pretty straightforward. But for later assignments, you're going to need to be actually thinking about, well, what can go wrong? And so when you're writing an interpreter, there's a lot of ways programmers can throw things at you that you never anticipated. Okay? I will bet most of you have probably thrown code at your compiler that the writers probably had not anticipated. We've all done it. So testing will be important for doing your own testing. So if you can, run the little prototype autograder that we give you against it. But if for some reason you're still having a problem getting that to run, it shouldn't be a problem. The TAs have their own autograder that they know, they've set up their own environment to be able to run it. Couple of sort of frequently asked questions with that. The biggest, so we're starting to see some questions on the Piazza group, which is great. Please activate your account there on Piazza and try to check that regularly. The biggest questions that come up now, which we're seeing, are, what I mean is they come up every semester, and so we're seeing the same kinds of questions. So one, make sure if you're getting a message that it can't find the Racket executable, make sure that that is in your executable search path. Okay, that would be your path variable under Linux or Mac, and then I know under Windows there's a more interactive. There's a GUI for being able to add something to your executable path. Also under Windows, and this seems to be something new with version 7 of Racket. The binary installs as capital R Racket and not all lowercase like it does under Mac and Linux. And so you might find it not being able to find it simply because it's calling Racket with a little r and you have an executable in your path with capital R. You can do that either by just tweaking the script so it has capital R, or just renaming the binary. I don't know what happens if you rename the binary, if that might break other things like Dr. Racket working. Which I know some of you have run into that issue. Which way did you try? Changing the script or renaming the file? Or have any of you run into it? Yeah.
Well, I have Windows, and I did notice mine was capital R,
Uh-huh.
but I didn't have to change it. It still worked.
Oh, it still worked. Okay. And I know you were meeting with the TA. Just the name of the executable, and that worked fine. That didn't break anything else. Okay. All right. Just be aware of that potentially if you're with Windows. So biggest issue number one is always just making sure it can find the Racket executable. The reason is there's all kinds of places you could choose to install that. and the grading script can't anticipate all of those, so it just calls out execute racket and then relies on you having that in your executable path. The second thing is many of you are seeing issues when it's trying to do the string compare of your output and the expected output. The big issue there, especially if you're seeing like a B before the strings in some of the messages or things like that, Python changed how it handles strings between version 2 and version 3. And so that's why everything could be working perfectly except for the string compare. And so you need to make sure that whichever version of Python you have installed on your machine, you're executing the corresponding script. So if you have latest and greatest Python 3, run the Python 3 script. If for some reason you're running the older version, and there are people who consciously choose to run 2.7 instead of 3.6 or whatever the latest is, simply because of some compatibility issues with various other libraries. If you're still on 2, run the 2 script. So those would be the two things that I would double check if you're having trouble running that. Any other questions? Anything else that you're running into? Yeah.
This is more for after turning it in.
Yeah.
Let's say we do fail a couple of the test cases. Is there a way to like make out and fix it, or just as is?
So if anything's breaking in the little prototype grader we give you, of course, fix that before submitting. But no, we won't. The TAs won't be running that until after the submission deadline. So you can, if you realize your own mistake, you realize that there's a case I didn't test for or I made a mistake in something, you can resubmit all the way up until the deadline. But and whatever you submit last will take. So make sure it's a complete submission. But then, but specifically to your question, no, there won't be a chance to sort of go back and redo those after the TAs actually grade them. So that's why I want to put the onus is on you all to test your own code. And I think sometimes we might do a little bit of disservice by, in early classes, just giving you the test cases for everything. It's not really how the real world works. And so part of what I want you to think about is, what are the tests, what are the things that my code should actually be doing? Sorry, I'm not trying to belabor the point. You'll see this more when we get to later things. I really want you thinking from a language standpoint, what are the cases that I need to be able to handle? But this one, the cases should be pretty straightforward. Yeah?
Is there instructions anywhere for how to set up the Python auto creator on Mac?
We don't have it set up, but basically it's just make sure you install Python and then download the script that we provide you. So if you all haven't seen it, if you go here, here's the script, version 3 or version 2. One thing with that, somebody mentioned they ran into an issue where they were copying and pasting from here, and it was sticking in some new lines or some other things like that. Probably best to just actually download the file. And then basically you would just invoke it by just Python, the name of the script, and then then as a command line argument, your file. Okay. And you can name that file whatever you want to. Okay. Any other questions? Any other issues you're running into? Yeah.
I was running into one earlier where Racket wouldn't recognize the function let, which is
Okay.
a weird case for me. There's losing the auto
Which version of, okay, so.
6 point something.
No, what I mean is did you change, so within Racket, so inside Racket, there is an ability to actually change some language settings, including some. Did you change that at all?
Yeah.
Okay. So you want to use just straight Racket, which it should be the default. So under choose language, if you do go to choose language, just choose the full Racket language. There are some teaching versions of the language. So for example, how to design programs, and we've got a link in some supplemental materials on the pages, just some information about that. It has different sort of student levels of the language. Think of this as different versions with increasingly less restrictive training wheels. It's just used for teaching. And it could be something like that. Because I do know in some versions of that it disables LED.
Yeah, I think that's what I did.
Okay, that's probably it. So use the full version and then make sure you have pound lang racket at the top. So you won't need to be doing this, but for racket, you can change versions here, but you can also change which version of the language it uses by putting a pound lang, kind of a pragma, if you will, at the top of the file. So if you just have pound lang racket, it'll be running full-blown racket. Okay, no training wheels. Any other questions? So I hope you found this first assignment to be a fairly straightforward one. Most of it was probably just trying to get Racket installed, figure out how to run the auto grader, work out any compatibility issues, putting a Racket in your search path, and so on. We wanted to just try to have a very simple assignment early on so we could get all those kinks out, and then hopefully things will just run smoothly from here. Now, just a heads up, every time we switch languages, you'll have to install that language and then make sure that language is in your search path. So that part you'll just have to repeat, but once you've done it for one, it's really easy to do again and again. All right, since I have this up, let me show you. Last time I introduced Racket and I did a lot of live coding, I probably mentioned that when I live code, it's a mess. Likewise, it probably is for you. In other words, when I'm standing up in front of a room trying to live code, I'll make up variable names. I'm not commenting my code. I'm maybe not necessarily indenting perfectly. And so what I do is I'll distribute after class, even before class, I will distribute through Learning Suite a cleaned up copy of what I live coded in class. And so this is the cleaned up copy from last time. You'll notice it walks through what I walked through last time, but it also has comments and maybe an example or two. So here's one more example that I didn't get a chance to time-wise at the end of class. So if you haven't yet seen these, just be aware, all the stuff I'm gonna live code, I distribute in cleaned up form. Okay. And again, that's just go to the content section in Learning Suite, go to the appropriate topic, and then that day's material. Questions on that? Had you guys already found this already, or how many had, out of curiosity? Okay, I hope you find it useful. And also you're not having to sit there trying to type as I type, trying to take notes. You can just focus on what we're building in class. All right. So we're going to continue on, unless you have any other questions. We're going to continue on with Racket. We're going to introduce lists and also how you process lists recursively. Now, this is basic stuff. You've seen a lot of these ideas before. You probably haven't seen it necessarily in Racket. You've all coded recursive stuff, but I don't know if you've really talked much about how to go from the structure of the problem to this recursive structure of the code. So we're going to talk about that as well. But we're also going to tie this back in to programming languages broadly. So that's what we're going to talk about today. Your next assignment will be using lists and recursion, and that's due on Friday. After today's material, we're going to talk about a concept of what are called first-class functions. The idea is functions as first-class entities in a language, meaning you can store them, you can pass them around and do other things, which might seem kind of odd. But remember, I said, because functions are code, right? You store data, but functions are code. Well, code is just data, remember? So we're going to talk about how you can actually leverage that and do some really cool things with what are called higher order functions, functions that operate on other functions as parameters or return values. And then that's going to be the next Racket assignment after that. All right, so let's dive in, unless you guys have questions. Anything? Okay. So I remember I mentioned that Racket derived from Lisp, and Lisp is, oh, sorry, let me back up. Hopefully you've also all seen, I didn't show in class, I hid this part, the definitions pane. I was just entering things interactively directly into the REPL. Obviously you don't want to code that way every single time. So hopefully you've all seen, you edit your code here, and whenever you click run, that just feeds it to this interactive pane. Sorry, it feeds it to this pane. You'll see it. It basically takes everything in here and feeds it line by line as if you had typed it in to the REPL. And then of course you can continue to interact with the REPL from there. So one of the really powerful ways of interacting with interpreted languages is have it run all of your definitions, and then over here you can poke and prod it by just calling specific functions and watching with specific inputs and watching what the outputs are without having to necessarily write other new unit cases. Are still good. I'm not saying it's not part of that, but when you're trying to debug, sometimes you might just craft specific test cases to test specific things. All right, so I want to back up here. Sorry, I was saying, so Racket derived from Lisp, and one of the, Lisp stands for List Processing Language, so we're going to talk about lists. But I want to back up first and talk about just types in general. So you've all used types in a language. You've seen different types in different languages that you've worked with. How would you define a type? What is a type in a language? Yeah.
Kind of like a named placeholder.
So a named placeholder, okay. In the sense that it can hold certain types of things, or, yeah. So it could hold certain things, yeah.
I was just gonna say, like, it's a restriction on what a variable can be.
Yeah, so when you associate a type with a variable, it's a restriction on what you can put in that variable. Okay. Now, some languages, by the way, require you to explicitly say that variable is this type. Okay, it's what's called manifest typing. Java does it. C++ does it. You may have noticed if you've ever programmed in Python and a number of other languages, there are many, though, that do what are called dynamically typed languages, which is you don't have to declare what the type of something is. And you can actually maybe even put different type, that variable could be different types at different times. Racket works like that as well. Now, one thing to keep in mind, just because you don't have to declare the type of something, doesn't mean that that variable doesn't have a type. It's just that it's not a permanent type attached to the variable. It's a type attached to whatever data that variable currently holds. You see the difference? Okay. There's a hand up over here as well.
I was gonna say.
That idea? Okay. So, that's a really great point. Some languages have what are called statically typed, sometimes even where you declare it. We're going to actually have a whole unit on type systems towards the end of the class. Some use dynamically typed. Racket is dynamically typed, kind of like Python that way. So let me share with you sort of a formal way of thinking about a type. So if you think about, you were saying it's sort of what values it can take on, what kinds of things you can put in a particular variable. But it also restricts what you can do with it, right? There's certain operations you can do with numbers that you can't do with strings and so on. And so a type can be thought of as, first off, a set of values. What are the valid values that some piece of data can take on, right? Ints and strings and so on, like to think of it that way. But also a set of valid operations that can be performed on those values. All right, so we're going to come back and look at this part later. But let's look at this part, set of values. So how can you define, what's the set of possible values for a character in C, C++? Sorry. All right, let's make it more specific. Unsigned character. What's the set of values? Okay. Right. So what numbers? Yeah, 0 through 255 for an unsigned byte. Okay. Now I can decide, does that stand for ASCII characters? Does that stand for numbers and so on, right? It's bit patterns. One of the things we'll get into later is this part of your types is actually association of bit patterns with different values. So unsigned byte or unsigned character was 0 to 255. By the way, small nitpick, as an old school C programmer, I think of them as, I call them, I say char and not char, mainly because I don't have strings that are made up of characters. Just so if you hear my usage, that's why. All right, so, but a lot of people I know will call them chars. So think about, all right, let's go bigger. Set of unsigned ints. Right? There's a finite number of them, right? Okay. It's 0 to what? 32, 7, 68. I don't expect you to remember that or memorize that. Sorry, 767. But the main thing is there's a finite number. I can just enumerate them. So you've got enumerated types where you can just enumerate a certain set of values. A lot of things have a finite number of possible values. Right? Let's think bigger. What, just mathematically, the set of all integers, right? How big is it? Infinite, right? I can't enumerate them all. So when I've got sets, I can actually try to enumerate them. Here are the members of the set. Or how would you define integers? Let's start simpler. Let's actually just go whole numbers, 0 and up. Okay? How could you define that set mathematically? Yeah.
Set of all natural numbers.
Okay. So, but how would I say the set of all? How would I define it?
Every whole number greater than 0.
Okay, so every whole number greater than 0. All right. So then, what's a whole number? So notice one way that he defined it. And we're actually going to see this later. A number of languages will actually define certain operations using all the members of such and such a set that satisfy some test. You've all probably seen that mathematically. Right? How else could you try to define it? So yeah, I can't enumerate. I could take some other infinite set and filter it out according to some test. But then you always end up with a chicken and the egg. Sorry, you're back to square one in the sense of how do you then define that infinite set? So let me give you, here's one example, or one way you could define it. 0 is a whole number, right? Okay. By the way, I always forget, is 0 whole number or natural number? Which one starts at 1 and 0?
Natural numbers start at 1.
Natural numbers start at 1. All right, whole numbers start at 0. All right. So 0 is a whole number, right? And then let's start, so I have some number, some value that's actually in the set, and then use a rule that says if something is in the set, then something else is known to be in the set. So 0 is a whole number, and then also a rule, if n is a whole number, n plus 1 is a whole number. You agree that that would work? So these are inductive definitions. You've probably seen them before in class. I'm sure in 236 they talked about induction. So we can use these to define concepts, sets of values. All right, let's go with another thing. The set of all valid linked lists in C++. Okay. Now how do you define it? And yes, there are infinite number of them. So how would you define it? How do you build linked lists in code?
You have like a root, and then if it links to another one.
Right. So you have a node, a root,
Yeah.
right? And that links to another one, another list, right? So you can say a linked list is a node that points to or links to another linked list. Okay? What's wrong with that definition?
It's recursive.
Well, nothing wrong with recursive. Okay? There's no base case. It never stops. Okay? So you can have circular definitions. You just have to have some way of bottoming out. And so we use this for all kinds of data types. Linked lists can be defined inductively. Trees, you all learned before, right? What's the definition of a binary tree?
It's 2 children.
Yeah, so a node with 2 children, each of which are
Well, actually, it could be up to 2 children.
up to 2 children,
Right.
right, for a binary one. Okay. So up to 2 children, each of which are what?
Roots of other trees.
Roots of other binary trees, right? Except you have to be able to bottom out. Well, sorry, it could have up to 2 if you don't allow the non-empty case. Another way is every node has 2 children, but a valid tree can be empty. So there's 2 ways of of defining that. Here's why we're talking about this. Here is another set of inductively defined data, or data types. Remember I said to your C++ compiler, your program is input data, right? What about the data type, the set of all syntactically valid C++ programs? Everybody agrees that's infinite, right? And all kinds of strange combinations you can't even think of, or shouldn't even try to think of sometimes. So if you're trying to process that data, you need to be able to define what that data is. Well, guess what? Programs are defined inductively. You've seen grammars, right? 236, 252. You've seen grammars for languages. You'll notice those languages usually are defined inductively. Here's something that you know is part of the language. And if that's part of the language, this is part of the language. And if this is part of the language, that's part of the language, and so on. So as long as we have languages that have while loops that contain for loops, that contain other for loops, that can contain a while loop, that contain an if, that contains another for loop, that contains a switch with multiple other while loops in it. By the way, don't ever code it that way. Break it up. But as long as it's legal in the language, you have to define the language inductively. And one of the things we're going to talk about with the remainder of the time today is the only sane way to process things that are defined inductively is recursively. So recursion might have appeared to be this interesting novelty that, oh, look, program functions can call themselves. Yeah, oh, it's a cute feature. No, for processing inductively defined stuff like programming languages, it's absolutely required. All right, so let's begin by just looking at lists and recursion in Racket. All right, so I'm just going to go ahead and hide the definitions for a moment. So every language has types. There are simple scalar types, which are things that contain one value. Now remember when we were talking last time, we talked about primitive things in code, literals and variables, some means of combining them, expressions, or statements in some languages, and then some means of abstraction. The same thing is true not only for code, but for data. There are simple types, we call them scalar types. There's a means of combination, ways of putting those together in more complicated data structures, and then a means of abstracting away some of that complexity. So let's start with, if you think about it, the simplest possible aggregate is to just put 2 things together, to pair two things together. If you think about it, going back to that definition of a linked list, it's some data, right, or more, one or more pieces of data, and a link to a next one. We're going to use that same idea to define lists. Right. So, yeah.
Back to the idea of scalar, that means like string, int, stuff like
Yes.
that. And then not
So-
scalar is like list.
Right, and structs and classes or objects and so on. Now, so int, float, character, those are all scalars. Strings, it depends on the language. Some languages will define strings as a scalar type. Some will think about it in C++, sort of just raw C-level strings. The arrays of unsigned bytes terminated with a null character. That actually, if you think about it, is an aggregate, it's an array. So strings can go one way or the other depending on the language. All right, so let's talk about lists. So we said a linked list is something followed by another linked list, right? But we said the problem was there was no base case. There's no bottom out. What is the base case for a list? Actually, let's go back
you
to
have a null
this.
pointer.
Pardon?
You have like a null pointer.
A null pointer, which represents, in essence, what kind of list?
An empty list.
An empty list. Okay? So null pointers are one way to do it, but the key thing is it's an empty list. So the idea is a list is either an empty list or something something plus a list, right? And you see, of course, there's the inductive step of it. So we're going to start off, we're going to define lists this way. So the way to make an empty list is the keyword empty. Now you'll notice it's going to print it out with quote. It's just simply saying this is sort of quoted output, if you will. And then parens with nothing inside. So it will print out lists in the elements of the list in parentheses. This is its way of saying an empty list. Parentheses with nothing else in it. The way to create a pairing of something plus another list is with a keyword called cons. So think of it as construct a node of or a pair. And it turns out that these are what are called heterogeneous lists, meaning I can put any data type into them. Sorry, they don't have to all be the same type. Aggregates can be homogeneous, all the same type within it, or heterogeneous. So I can put anything in here. And so if I do this, what do you think I get back?
A list with one element.
Yeah, I'm going to create one node that contains one and the empty list. And if you think about it, that's just simply creating the null and the one. Okay? Same way you might draw a list. Can you guys still see this if it's this low on the screen? Okay. All right, now I can repeat that. So const just simply creates one node and pairs one piece of data with another list. Okay? So what's this doing? What's this going to return? Const 2 onto the result of const 1 onto empty. So it's just this list. Okay? And I can keep doing that. So const can be used to prepend one thing to the beginning of an existing list. Okay, so it will create a node, a linked list node, the rest of which is some other existing list. Now, this gets really laborious if I'm trying to type longer lists. So there's a shorter way. I can just type keyword list. It's variable arity. I can give it as many parameters as I want to. It counts the parameters, creates that many nodes, and puts the data in one by one. Okay? So list 1, 2, 3, 4 will make the list 1, 2, 3, 4. So now we can build lists. Let's give that thing a name so we can keep referencing it. All right, so now I ask what A is. It's list 1, 2, 3, 4. So if you think of operations we do on lists, I want to start accessing contents of the list. Lists are always accessed from the beginning. So in this case, we've got A. Sorry, I will move out of the way in a minute. Okay. So A is the list 1, 2, 3, 4. The way I access the first thing in the list is the keyword first, or operation first. Okay. Rest will give you the rest of the list after the first thing. So in other words, if I look just at this first node, A, this first gives me the data, and rest gives me the second part of that node, the next pointer, if you will. Okay. All right, so I get 2, 3, 4. How would I get the second thing? Yeah?
Does it only give you the rest of it if you already said first, or does it always just give you everything first?
Yeah, no, I can use them independently. So first will get me the first thing, rest will get me the rest, but I don't have to have done first. How would I get the second thing? Yeah?
Say first, and then in parentheses rest. Okay?
Yeah, get the first thing from the rest of the list. And that's the second thing, right? How would I get the third? If I'm just trying to access it directly.
Just third.
Okay. By the way, there actually is a keyword. There are abbreviations first through about 9th or so, but this breaks down. I just wanted you to see that the idea, though, is you can keep following the rest to get to whichever node you want, then access first. Okay. All right, so let's start writing code to process these things. And that's what we'll do with our remaining time. So let's bring back up the definitions here. Let me run this to clear it. All right, so let's just give ourselves a list that we can use for testing things. All right, let's write a function that computes the length of a list. So, how do I define a function?
Define.
Keyword define. Let's call this thing len, short for length. And I often like to use LST. Be careful not to write LIST because it thinks that's the operator list. All right, so define the function that returns the length of a list. What do you do? Yeah.
One thing that you could do is you could just, you can count the first item, and then, I don't know, you could give it a parameter that's like count or something
Okay.
like that. And then basically every time that you call length again recursively, you increment that counter.
Good.
And then when it's finally, when there's nothing left in the list, then you return.
So you've actually hit on a way of coding it that's called tail recursion, which actually if you write it in that fashion, it's actually amenable to something called tail call optimization that we're going to talk about. I don't know if we'll have time to today, but that's one way to do it. And by the way, I show it actually in my notes. That's another way to do it. Let's try it first without a counter, though. Okay? So if I give you a list, what are the possible things that could be? What's the definition of a list?
Could be empty.
Could be empty or it could be a node, right? So one of the things you were saying is I could count the first one, right?
Yeah.
What if there isn't a first one?
Just put that in the base case.
So the first thing you always want to do when you're writing recursive code is test to see if it is one of the base cases. Notice I said cases. In some cases, there could be more than one. All right, so if there's a predicate, by the way, empty question mark, test to see if something's empty. If the list is empty, what's the right answer for the length of it? 0, okay? So far, so good. If it's not empty, what must it be?
Length.
One node that contains one thing. By the way, the length of that is 1, right? And so it's one thing and what?
Like the rest.
Another list, right? Okay, and yeah, we would then compute the length of rest. So there's a process here, and let's code it first, and then I want to talk about the general process. All right, so the length of the first node in it is 1, right? How would I get the length of the rest? Recurse. Okay, that's the very function you're currently writing. Once I have those two, what do I want to do with them?
Add them.
Add them. So in other words, 1 plus the length of the rest of the list. Oops, okay. All right. So notice the structure here. First, test for the base cases. If it's not one of the base cases, then break it apart into its pieces, because it's an aggregate that's been put together and put together inductively. Break it into its pieces. So here you have first and rest. Those are the only two pieces of these nodes. And then process the first, process the rest, which is usually recursively, and then put the pieces back together in some form. So notice that structure. Test for the base case, but if it's not the base case, break it apart, recursively process the part, or potentially recursively process the parts, then put them back together in some form. This is the same algorithm that you probably learned for recursing through trees or other kinds of things in 235. Did they put it that way in terms of break apart, recurse, put back together? Did they? I'm just trying to calibrate.
It's been a couple of years.
Been a while, okay. All right, so let's write other things. I'm going to write some other functions here. And we'll just use the rest of our time to keep writing some variants of this function. Let's write a function that will tell me if all of the things in a list are even. Okay, so where do I start? I'm going to give me a list of numbers. I'm going to tell you if they're all even.
Check if empty.
Okay?
Copy.
Test for the base case. Yeah. If I could only type on a Monday morning. All right. So, if it's empty, are they all even or not?
Yes.
What's the right answer? Yeah, it turns out mathematically, you can argue about this. Mathematically, you can argue that it's true. Mainly because all can be defined as there does not exist one for which the test fails. Does that make sense? So in other words, an empty list, there does not exist one that's not even. All right, and you'll see why this is important with the recursion. Now, what do I do if it's not empty?
You have to go through it.
Okay.
Sure.
So I have a first and a rest. The first thing is a number. What do I want to do with it? See if it's even, okay? Is the first thing even, right? Now, so that, by the way, if it's false, I can just stop, right? But if it's even, All right, if the first one is even, how do I know if the whole list is even?
Because the rest.
Yeah. Determine if all the rest are even. Boy, I wish I had a function to tell me whether everything in a list was even. Okay. Well, if you think about it, that's what you're writing. And this is sort of the leap of faith with recursion. All right? When you get to a point where you need the very function you're writing, you just call it. And if you if you follow the kind of the recipe for this, it will work. So we want to see if everything in the rest of the list is even. Now, I've determined if the first is even. I've determined if the rest are all even. What do I want to do with those two results?
And
They're both Boolean, so
And.
and them together. Right? Oops. All right, let's make another list here just to test this. Okay. All right. So this tells me if they're all even. What if I wanted to, so first off, any questions about this? Do you see the process of going from the inductive structure of a list to the recursive structure of the code? Yeah.
So will you return nothing if default to false?
Pardon? Yes. We're going to say if the list is empty, we'll return true.
Okay.
Now, I just want to ask you some variants on this, and we won't have time to code it, but they're in the stuff that I distribute. What if I wanted you to give me back a list of which ones are even or not? How would the code change? Actually, we can do this one pretty quickly. All right. So, what if I wanted